lang. Okay, I hope you are watching this lecture. This is a review on analogical dynamic systems. We would like to analyze the analogical dynamic systems based on equivalent electrical circuit system. Okay, so meaning what we have learned in electrical circuits, we can apply it to analogical dynamic systems. Okay, the contents of this review is first the derivation of analogical dynamic systems, and also the explanation why is it we call it analogical. And second, we would like to do a generalized RLC circuit analysis using phasor forms in S domain. And also we here in this part 2 we will solve some problems, maybe 3 or 4 problems. Okay, if you have questions you can write in the comment section. Okay, let's proceed with the first part, the derivation. So actually the thing that you're seeing now is a work of this is a work of one of your classmates, and um, it's the work of one of your classmates in the class, no? So sorry, I'm adjusting the scale. Okay, so here you can see the different systems, no, how they are derived. So this is the work of Miss Aubrey Tidoso. So I presented this to you so that you can also see how to derive the second order differential equations. Let's first discuss the acoustical. Okay, so the acoustical is very simple. You have here the pressure and then the x dot. Okay, so the capital X dot meaning it means the it's like the signal, no, of or the strength of the or the signal strength of uh, uh, the acoustics, no. So although we're not familiar with acoustics, you can see that the source, which is the P, okay, and the rest you have the pressure of the RA, or the acoustic resistance, and you have the um, CA, and you also have M, no. So they have all of them have physical meaning, and we have this equation, okay, comes from the some principle, no. Actually it's very simple. It comes from the energy conservation. In circuits we have this Kirchhoff's law, no, summation of voltages is equal to 0, or KCL, summation of currents, is equal to 0. Basically all of them comes from the idea that energy is neither created nor destroyed. And the same also for mechanical rectilinear. I think this one is quite familiar to us. The Fm here is the applied force. So if you have a block with a mass m, and then you have the spring Cm, and then you have the here you have the friction or we call it the mechanical resistance. Okay, and yeah, so this is the spring. So if you can remember for your spring, um, I think you, K, you can remember K, the spring constant, and the unit of this is Newton per meter. Sorry, Newton per meter. Okay, so later there's an example of this. We can analyze this system using the Phasor or in S domain. Okay, so take note of this. But cm is actually the unit for your cm. If you check your previous lecture, this is centimeter per dyne. Okay, and which is actually the inverse of k. So meaning k is actually equal to 1 over cm. Okay, so but if you want to convert that one to electrical, cm is like the capacitance, no? Capacitance. So later on we will see. Uh, okay, so going back to acoustical, so PRA, so the pressure across the acoustic resistance is actually RA times X dot, and the pressure in the M. So I cannot give you a physical description of this. Maybe we will proceed to rectilinear. Okay, I think this one is easier than the other system. So FRM is the um, force in the resistor or the friction, no? So actually this is the friction force. So Rm times X dot. So Rm is actually uh, this is the unit of Rm. The unit of Rm is dyne per centimeter second. So this is actually the unit of Rm is equal. The unit is dyne per centimeter per second, which is actually the same as Newton second per meter. And if you try to cancel it out, where Newton is kilogram meter per second squared, and then you have the S, and then divide by M, you have cancel, 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 cancel. I think this is meter squared, so you have equivalent kilogram, sorry, mass times Newton is mass times gravity. So sorry, this is only M. So kilogram times second divided by second. So you can think of it as the momentum. Okay, it's like the momentum. And then if you multiply this one with x dot is simply the velocity. Okay, x dot is the velocity. Okay, so multiply with velocity meter per second, and then this becomes now we have kilogram meter per second squared. So this is actually the momentum. Okay, this is the velocity and this is the momentum. Okay, and this one is kilogram per second. This is the I forgot the definition of this. Okay, so but you can see that they have physical definition. Okay, so that's the important thing here. And then we proceed with the m dx dot. So meaning the x here, x dot, velocity. So meaning x is the displacement. Okay, in meters. So in the standard unit is meter. But you can find in the book that you are using centimeter because some of the values are very very small. No? But you can have standard unit. The most obvious here is the m dx dot over dt. Dx dot there is actually the acceleration. Okay, so meaning Fm is actually equal to mass times acceleration. Okay, so this is the weight of the block. So basically that is your inductance. Okay, so because this is equivalent to this is dx dot over dt, and this is equivalent to L di dt. where I is also the Q over T, so, or charge per second. Here you have the meter per second, right? There's a charge per second. So that's why we call it analogical, because L here becomes mass. Okay, I hope you get the point, no? So they are equivalent. They're not the same, okay, but they are analogical. So meaning you can substitute L with M and I with X dot. Okay, so they have uh, okay, but assuming that you replace everything, no, all the elements, but analogical in that sense that you can use the same analysis, okay, because they have the same, this is in the first order differential equation. And then the other one here, uh, Cm, okay, this one here, actually this is, as I said, that's uh, Cm, the unit of Cm is sine per dime. It's actually K, 1 over Cm, and the unit of this is Newton per meter. Okay, so sorry, the unit of that is Newton per meter. Now, what is the force? If you have a spring, yeah, you can see that this is a spring. The force of the spring is kx. If I'm not mistaken, this should be kx. Yeah, that's kx. That's a force, because this is the unit of this one is Newton over meter, and then multiply by meter. The x is the displacement, so cancel. So the unit of this one is Newton, so that's the force. The force exerted by the spring, no? So if you are exerting to the spring, the spring will respond the opposite direction, no? So if you add, if you force, if your Fm goes this way, so the force of your spring is opposing to that force, no? So that's why we have the action reaction. Okay, so that's why if you have this expression, so that if you have negative Fm here, this one is positive. Okay, and the same also for Rm. Why is it positive? Because if you exert force there, Rm will the friction will exert force in the opposite direction, and the same for your spring and also your mass. Okay, this one is for the mass. Okay, so I hope you understand the analogical, no, analogy. So you have this usual system, okay, and then the force Fm. Okay, so I hope you understand already this analogy. Okay, so you may want to study more in the book, um, but it's quite simple if you understand the physical sense. And the same also for the other side, for the mechanical rotational. Fr is actually torque. Torque is Newton meter. Okay, T is equal to force, uh, force T. Okay, so if you this is your, if you have a fixed point here, and then you apply, and then this is a rod. If you apply force F and with a distance D, okay, so the torque is a force distance, no? That's a kind of measure for rotational force, no? We can call it rotational force, but popularly known as torque. So, and I think I'm not that expert in the physical sense of this, but you can think about similar case for the rectilinear, wherein CR is a kind of spring, but the spring that is based on rotation, no? Do you I think you know a device that if you try to if you exert a rotational force, and then it will, and if you remove the force, it will go back to its original position. Okay, so have you encountered that kind of device? One common example is the door. You have a door that returns to its, um, for example, you have a door. uh, okay, so this is the that's the door, and let's say this is your, okay, and okay, diba? If you, okay, so the door, if you push the door this way, and then there's a device here that that keeps the door normally closed, keeps the door normally closed, meaning if you remove, if you enter already, and then if you remove your force pushing the door, if you remove that force, the door will go back to its original, to its original position, which is normally closed. The door is normally closed. So that system is actually can be expressed, it's like a spring, but the spring, this one here, the spring is based on the angle, no? It's like a spring that is, so this one, if you rotate this one here, and if you turn half cycle, then remove the force Fr, the spring will exert a force opposite to that direction, so it will go back to its original position. Okay, so basically it's just a rotational spring. And then you also have friction, torque friction, okay, based on the contact points of the bearing. And then you have the weight, I think, inertia, no, the weight of your, I think if you have a, if you have an inertia there, uh, um, so remember, if you have this, if you have this wheel, okay, if you try to exert force very fast, you notice it's very heavy, no? But if you force it a little bit slowly, okay, so inertia, I think you know the idea of inertia, meaning, um, because of the mass, di ba? If the wheel is very light, so there's no problem, no? So there's no problem rotating the wheel. But if the wheel is very heavy, so because of inertia, if you try to turn, if you try to rotate, exert a force, a torque to to this wheel, it's a, there's a opposing force, no, because of the mass. Okay, okay, because of the mass, the friction, and the spring. Okay, so you can have many systems like that, no, and expressing into these three, um, you have, actually this is only a 1 or 2 degrees of freedom. Okay, uh, and it's acoustical, and that's also a similar case, no? So, and then let's proceed with how do we derive the second order differential equation. So we find it in the book, this one, but it was not derived there. Actually, you have, let's proceed with rectilinear. So you have Fm, the, if you exert a force going to the right, the rest will exert force to the opposing to that direction, so which is to the left. So you have here, no? So, and they should be equal, because the external force, I mean the energy, no, you can imagine the energy you exert to that block is the same energy that you receive, no, okay, or the response. So you have this summation, okay, then you have this integration, which is quite similar to what we have solved in electrical circuit, no? So you have the V is equal to, Vs is equal to Ri plus L di dt. Okay, so I think I can replace this I with small I, thinking that this it is in instantaneous current. Okay, and then 1 over C, integral of I dt. Okay, um, you can also replace this one with charges. Okay, and we know that this one leads us to d squared I over dt plus 1 over LC, uh, R over L di dt plus 1 over LC, and equals to Vs. And since if Vs is constant, okay, here you can see here similarly, if Fm is constant, then this will be 0. So meaning you only have the system without a force, okay, without an applied force, meaning you only have a uh, natural response, and there's no force response, no, because you did not exert a force. Because if you exert a constant force, the system will not react. I mean, the system will react um, if you have this expression 0. The graph of that is simply uh, if you remember, it depends on the value of m depends on the value of RLC, no, the value of RLC. You can have a damping, the three types of damping, right? If you can remember, you may have a undamped, or you can have a critically damped, or you can have a overdamped. Okay, overdamped. Okay, so you have three possible damping types, no, depending on the value of your R, L, and C. And here in the mechanical rectilinear, depending on the value of your mass Rm, mass Cm, and the friction Rm. Although we are familiar with K, or coefficient. I forgot the coefficient of friction. So Fs, that's a force of friction. I think Ks. Okay. So anyway, so you have those. Um, these are the given of your system. So if you want to model a system, you need to define these parameters. Okay. So if you want to construct a system, you need to define the parameters. Here you need to define the, okay, what is the rotational spring, or the friction here, what is the friction. So if I'm going to use a bearing, okay, so you need to define the RR, okay, and then also the mass of this wheel. Okay, the same is also true for your acoustical. For example, for your earphones, or for your speakers. Okay, now the good thing with these systems is that you can actually make a later on in the advanced circuit or advanced control system, you can actually make a cascaded system. What I mean with cascaded system is that, okay, you remember that you have an electric fan, for example, and first you have the electrical system, electrical, okay, because you plug it to the socket, no, so you have the source, electrical source. Maybe I can make a more. So you have electrical first, and then you have mechanical, right? So the fan rotates, and then if you notice, the fan emits sound, okay, and there's acoustical, and actually this is one of the simple system. Now take note, electrical, mechanical, acoustical. This is also the same as your some types of your earphones. So there's a mechanical part. There's electrical, first the source, and then you have the mechanical, the vibration of the um, speaker. So if you're going to work in Knowles, Philippines, no, so you have this process, no. So you have you have a small speaker, and you will see that because of the vibration of, okay, vibration of this part due to electromagnets, no, because of the attraction of the metals, if you change the magnetism, so the metal vibrates and gives a sound, okay, it will give you a sound, and you can express all of these in one system, okay, in one system, meaning although the source is in voltage or current V or I, you can actually transform everything into a unified unit, and you just simply put efficiency. For example, the efficiency here of conversion efficiency is equal to 0.90 or 90%. Okay, and efficiency here is 50%. Okay, or zero point 0.5. So meaning, because there's the energy is, if we are going to measure the electricity or the energy, so if we're dealing with efficiency. But you can have, if you're dealing with mechanical force, you can use the loss, no, uh, conversion loss, or etc. So well, uh, well, that's more advanced now, no, but the most important thing is that you've seen the analogical approach, no, the among all systems they can have similar way of analyzing. And then given the second order differential equation, you can now solve using what we've learned in circuits, the, for example, the Phasor and Laplace transform. Okay, so let me proceed with the generalized RLC circuit. Okay, so far there's no question. So okay, using S domain. Now, if you notice, all of these do have time domain. Okay, you notice this is dt. Okay, dt. These are in time domain. Time domain. Okay, this is also time domain. Okay, now depending on the source, here is constant, so that's why it's 0. So depending on the value of your source here, P, Fm, Fr, if you can represent the source with any signal, that's why in the book we use here Fm e to the j wt, which is actually the same as Fm cosine wt. Okay, if you can remember the transformation of the e to the j theta is equal to cosine theta. Okay, so if you have 2 here, so you have 2 cosine theta. Okay, so here in the book we express a signal Fm as a cosine waveform. Okay, so if you apply that waveform, what will happen to your mass? So it will go this way and go right and left in a sinusoidal manner, or in a waveform manner. So at this part here, it will be pushing the mass. At this part here, it will be pulling the mass, no? So you have that kind of signal. But and then the x dot here is the velocity of your mass. Okay, that's the velocity of your mass. And we can have that example, no, later. So that's it. And how to analyze these systems? We analyze this using the S domain, no, because in time domain it will be very difficult, no, if we're using time. And then although second order is still valid, you can still solve it. You can use numerical methods. So the more complicated the system, the more the number of order. So nth order ODE differential equation, no. So the more the the more the degrees of freedom, the higher the differential equation. The higher the order, no. So so in time domain is quite complicated. Okay, so therefore we have this new. I mean, it's not new anymore. It's a century old. But we have the S domain. Okay, we transform the time domain to S domain, and we can solve that one. So I'd like you to to solve this circuit, we can solve this circuit using a time domain. Okay, now we're given with circuit here. Later we will have an example for your mechanical. Okay, so mechanical rectilinear system. So here we have a two mesh circuit. So you have a this circuit, no? And we know that we can express this inductor and inductor, capacitor. So we can convert that one directly. The best way to solve this problem is to redraw. Okay, given transforming it to, the first step is transforming it to phasor. Okay, uh, okay, transforming it to phasor. So we can redraw the circuit. And then, so it's good to redraw the circuit so that um, you can visualize the. Okay, I hope you got that. So the first step, no, and then convert everything to phasor. So meaning in time domain V1, we convert V1, so becomes V1 is equal to 6 angle. What is the phase angle here? 0. Now you might wonder, where's the omega? Omega doesn't change, okay? Because it is the system. If you can remember the S is equal to alpha plus j omega. So that is the root of the system, no? That is the root of the differential equations, meaning your system's characteristic can be expressed by W, but it's not the concern of the analysis, no? The problem here is looking for VA. So VA, where's VA? Okay, so this is the VA. So because you have the ground here, actually put the ground. So VA is with respect to the ground. So this is actually VA. Okay, and the omega here is common to everything because they're one system. So if they're one system, it doesn't mean the other one has different frequency. The current here is very slow and then the current here is very fast. No, it cannot be. So they should be in the same how you call it, the same frequency. Okay, so that's why in our household, so the frequency at what you're experiencing now, 60 hertz in your devices that you're using now. If you're charging your phone or whatever, you're using your lights, it's 60 hertz. That's the same frequency in another house, in your neighbor, or in the place 1 kilometer away from you. So they have, maybe your frequency instead of 60 hertz, 59.98 hertz. So whatever frequency you have at your home will be the same throughout in your room, in your house, and also in the rest of the community where you have the same electrical circuit. But in Mindanao, if you go to Mindanao, at that instant it's not the same because they're not yet connected. Although there's an ongoing construction of connecting Luzon, Visayas grid with Mindanao grid. Actually, whatever you're experiencing now, the frequency there may be the same as the frequency that we are having here in Manila, no? But of course, some isolation. So anyway, so it may not be the same. Okay, so may not be the same because there are some isolation possibilities. So that's more advanced in power system. Okay, so the first step is to convert everything to phasor. So we have here 6 angle 0 degrees. And how about the voltage as V2? V2 is equal to 1 angle 60 degrees. Okay, this is 1 angle 60 degrees. How about the inductor? The inductor, we know XL. Okay, so actually the impedance of inductor is JXL. Okay, so which is equal to JWL, which is equal to J Now, if you notice, the W is 2 pi. Actually, if you can remember, this is actually S. Okay, SL. Can you remember this is SL? If you can recall actually this is, okay, I can, actually, the main idea here is SL. Now, S before is alpha plus J omega. Okay. Now, here, the source is only cosine. There's no e to the alpha t, right? So if your v is equal to wt plus theta b, then you have alpha. So the s here is alpha plus j omega times l. Okay, but you see, our given here is purely AC or cosine. So meaning your source here is like that. Okay. Now, what if your source is like this? That's what we have solved in the previous lecture, no? So you have um, the signal here looks like this, no? It can be like that. Okay. If you remove this expression here, you will have this expression like you have sinusoidal, no? So for DC, we remove this one, and also this one, we remove this one. Okay. So uh, the alpha and the omega is equal to 0 in that sense. Okay, so therefore the value here is only the magnitude, which is equal to 1 for DC. For DC, you have a straight line at 1 volts, 1 volt. Okay, so that's very simple. I hope you get that point. Okay, so therefore our expression here for AC signal is simply um, JWL. Okay, so you have J times 2 times the inductance, which is 6 hertz, and this is 12J. You can treat this one as an resistor. If you remember your prelim, or in the first part of this class or the set of classes, you see you have a simple DC all resistor. Okay, you might as well use the same idea, but this time instead of resistor, you simply replace J12. So this follows the Ohm's law, no? You remember V equals IR. Here we are V equals IZ. Although they're not confusing, they're not conflict with each other, but Z is R plus JX. Okay, and for general term, Z is equal to R plus JXL minus XC. Okay, the inductive reactance minus the capacitive reactance. So we also discussed this one in one of the lecture. Okay, so but so far we don't need to go that deep. Okay, so you have J12 and also the capacitor. So for the inductor here, for the capacitor, so you have 1 over JWL. Okay, so you raise J to the numerator, it becomes negative J, and sorry, this is C. That should be 1 over JWC. Sorry, I think W is 2 rad per second. Okay, so you have uh, 1 over J times 2 times 1. So this is therefore negative J 0.5. Actually, you can write ohms. Okay, so because all of them are impedance, or we can call it the reactive resistance or something like some sort. Okay, and the other one 0.5 F, the other GC2, you can call it GC1, is equal to, or this is XC, negative JXC. You can also call this JXL. Okay, you want, so that the reactance. Okay, so this is 1 over J times 2 times 0.5. So this is therefore negative j1, no? Okay, 2 times 0.5 is 1, and 1 over j is negative j. Okay, so j, you might wonder, what is j? J is imaginary number, okay? So you might, this one is j, the other one is 0.5, negative 0.5 j, and then the other inductor, which is 4, jl2 is equal to jwl2, okay, which is equal to j times 2 times l2 is 4. Therefore, this is 8j. So therefore, you have 8j. So having transformed everything into that circuit with phasor equivalent values, so let's proceed to the next part to analyze the circuit using whatever way, no, to find the value across the voltage VA. So how do we solve that one? You might wonder, we can use mesh analysis, which is okay, um, or you can use the nodal analysis, because you can see that the value here is V2, then the value here is V1. Okay, so if your ground is here, so V is equal to 0, therefore here is V2. Given the polarity, you have V1 here. Okay, so therefore you can construct like this. Sorry, I can redraw the circuit, but you don't need to redraw, no? So this is VA, so you have here uh, V1, and then I can replace this one with that one, so to emphasize then V2, then you have VA, then 0, and then you see this impedance here, we write J12, sorry, positive J12, and then we have here negative J, then we have, if you notice, I combined the two because this is the capacitor here and the inductor. They are connected in series, so you can add both of them, but they have the same opposite polarity. So 8 minus 0.5, so this becomes, okay, I can write 8 J8 minus 0.5 J. Okay, so this is 7.5, and then okay, so summation. So first step is transformation of the given. The second step is analysis, so which is using the using nodal analysis. Okay, so you have VA. Actually, you go back to the basic, which is the current going out is equal to 0. So you have I1, I2, I3. Okay, so therefore I1 plus I2 plus I3 is equal to 0. And then I1 is simply VA minus V1 divided by the impedance, which is J12, plus I2, the one in the middle going to the ground, VA minus 0 divided by 7.5 J, then plus VA minus V2 divided by the impedance in between, so you have negative J equals to 0. Okay, so check the equation. So how many variables? We only have one variable, which is VA. V1 and V2, they are given. Okay, so 6 angle 0 and 1 angle 60. So basically we can solve already VA. Then step okay, so you have actually 2 step lang, no? So in the step number 2, you just analyze and solve for the value of VA. Okay, so then you have VA, you can just 1 over J12, okay, So I hope you see where 1 over j12 is, and then plus 1 over j7.5, okay, for the second term. And then for the last term, 1 over negative j, and then all the other constants, v1 over j12 negative, so it becomes positive. So the one here, okay, so v1, that's negative v1 over j12 transpose becomes 6 angle 0 divided by j12, and then 0 over any value is 0, so the 0 here is ignored, so it doesn't add. And then this one here, negative v2 over negative j is positive v2 over j transpose becomes negative, okay, or you can write yeah, negative v2 over, now to for you not to be confused, negative v2 can be plus v2 divided by negative j, okay, but basically that's the same as minus v2 over j. Okay, that v2, we just replace this one with 1 angle 60. Okay, and can you solve already for VA? Very simple, you can use your calculator. So you have 6 angle 0 degrees divided by j12 minus 1 angle 60 degrees divided by plus negative j, and then the denominator you have 1 over j12 plus 1 over j7.5 plus 1 over negative j. Okay, and then your answer is in Pacer form, and then you convert that one into VA in time domain. Okay, so we can try solving it using our calculator. I hope you can actually use your calculator. Let me show you my calculator. Okay, so I have here my calculator, and you have mode complex, so mode 2. Okay, so you remember you have a complex form here, and then since they are in fraction, so I do that way. Then 6 angle 0, I hope you know how to do it, then divided by, oh sorry, so let me solve it first, and I will show you how it was divided by 12i 0 plus negative I, and then 1 over j12 or 12i, and 1 over 7.5i plus 1 over negative I. Oops, sorry, I think I made some mistake in my calculation. 4.5 for Henry, 2 rad per second, 8. Okay, just a moment. J.58, 1 negative j, 1 farad, 2 j8, j12, negative j, 12j, 7.5i, negative j, 0, 2t, 6 angle 0. Sorry, I'm in radian mode, so that's why. So that should be careful with your region mode. Okay, so I'm done with the calculator. So you can see here the value is 1.1055, or that's basically the answer is 1.11 sine 2t. So what I did, uh, I have this expression here. Okay, so you can see the expression 6 angle 0 over 12i plus 1 over angle 60 over negative I, and then sa denominator uh, you have here 12i, 1 over 12i plus 1 over 7.5i plus 1 over negative I. So if you press enter, you have a uh, 1.1055, but you can convert this to Pacer form, which is the one I presented to you. Okay, so we're going to write this in our answer. So you have 1.11, so then angle 90 degrees. Now take note, the final answer is in cosine because your sources are in cosine, right? So the answer should be 1.11 cosine 2t plus 90 degrees. Okay? But what's but? Okay, so cosine 2t plus 90 is actually equal to 1.11 sine 2t. Okay? So which is the same as our final answer. Okay, so I hope you get the two steps. Okay, so given our techniques in the previous class for the using nodal or mesh analysis, and then you have the Laplace transform, and then using the Pacer form, and it's important to know the physical indication so you can solve more problem. So okay, so I hope you find it easy at this point, and let's try another circuit. Now here the problem is to obtain the current ratio I1 over I3. So basically the goal here is to get the value of your I1 and then I3. Okay, now if you notice the values in the inductor and capacitor, they are already in reactances, meaning they're in ohms. So so here the L is not anymore given, and also the capacitance is not anymore given. And very simple, actually this is already converted into the second step, no? So you can actually since we're dealing with current, okay, and then you can see the loop. So at mesh 1 or I1, so you have negative V1. So notice there's no value for V1, so later you will see that this will cancel out, plus J2 I1. So the voltage across inductor is this XL times current I1. Okay, plus 5, that's a resistor, so that's 5, it's a real number, then I1 minus I2. Okay, you've learned why is this so, because there are two currents entering that, so this is equal to 0. Okay, you can arrange this equation, so you have I1 which is equal to 5 plus J2, and then you have I2 plus I2, which is equal to negative 5. So this is your first equation. Okay, and at mesh 2, okay, so that's your first equation, mesh 2. So you have 5 I1 minus I2. Okay, so sorry, I2 minus I1. So because we're in the mesh 2, so current I2 is positive. Then minus J4 times I2. Okay, and there's only one current entering this capacitor, then plus J2 times I2 minus I3 equals 0. So you arrange this one, I1, all I1, so negative 5 plus all I2, so 5 minus J4 plus 2J minus J4 plus J2, and then plus I3. I3 is negative J2 was 0. Okay, so you have this another linear equation. Then at mesh 3, you can do it here, mesh 3. So you have I3 here passing through. We have J2, J2 times I3 minus I2 plus 5 I3 equals 0. So we have this expression I1, there's no I1, so this is I2 negative J2, and then plus I3 5 plus J2. Okay, so you have three equations. So I can write 1, 2, 3. And our goal is to find I1 and I3, or I1 over I3. Okay, so how do we solve that? Okay, very simple. This is only algebra. So basically, actually we can just simply use, if you notice, we can use the two equations here, replace I2 here with I3, I2 with this equivalent here, and then you will have this in terms of I3, and then okay, but the usual process is to find I1, all I1, I2, I3. Okay, but you cannot use complex number in solving using your calculator. So we need to analyze how to solve it efficiently or faster. So I saw that this one can be a better way. You can also use the two, this one here, and replacing I2 with I1, so that the remaining equation will be in terms of I1 and I3. If you replace I2 with I1, so you can analyze, you can find a way to replace I2 with I3, and then you can solve for I1 over I3. Okay, so replace that one. So we have here we can using equation 3. So you have I2 is equal to transpose I3, so this becomes negative I3 5 plus J2. We have one more, to give you more idea. So we have one more problem here waiting, but we're almost done with this problem. Okay, so divided by negative J2. So all of these in complex numbers. So you have I2 now, then in equation number 1, okay, so you have I1 5 plus J2 plus I2, which is now I3. So so we can write negative 5, okay, minus 5 here, this is minus 5 I2, so 5 I2, which is I2 becomes negative I3, 5 plus J2 divided by J2 equals 0. And then you have two terms, transpose the other one, and you have the one on the left, and then you can cross multiply. Our goal is to find I1 over I3. So you have I1 here, just remain I1, 5 plus J2, and then transpose the other term. This is one term, right, in your algebra. So transpose that one, becomes positive 5 times the one inside, so this becomes negative 5 I3 times 5 plus J2 divided by J2. Okay, so we're almost done. So cross multiply the I3, so that's what This coefficient can be put in the denominator on the other side, and then I3 bring to the denominator of I1, and you have I1 over I3, which is equal to negative 5. Okay, what remains here is negative 5 times 5 plus J2, and then J2 in the denominator times the 1 in the coefficient of I1. So you have 5 plus J2. And then what would be the, using your calculator, I think you can solve it. You can try solving it, okay, as a practice for you. 5 plus 2i divided by 2i times 5 plus 2i. Okay, I think there's a mistake in my answer. I think there's something wrong. 5 plus J2. I3, 5 plus J2. 5 plus J2. Okay, we forgot the negative, the denominator. Okay, here. I think we forgot the negative, so that would be negative. So cancel the negative. So transpose becomes positive, and yeah, that should be positive. Oops, there's something wrong. Just a moment. I think we made some mistake. Negative J2, negative J2, negative 5. So that's I3. In the first equation, you have 5 plus J2, right? Negative 5. So negative 5. Actually, you can cancel the 2, right? Here and here. So they have the same. So negative 5 over J2, 2i. Okay. I think I made a... But my answer is 2.5 angle negative 90. 5. So this should be positive. 5. Let me check which one is incorrect. 5 plus G2, negative 5. 5 plus. Sorry, we forgot the V1, no? Oh, no. So we forgot the V1 on the other side. There should be V1 here. Oh, no, I think we made a mistake. Anyway, so we don't use the expression in 1. We don't need to use this because there's another variable V1. That's why we could not find the correct answer. So based on this solution from the book, so I think we can, instead of using equation 1, so I think we missed the V1. We can use the one in the second equation. Okay, so sorry for that. But it's good to learn from this way. We just made a mistake of we forgot the V1, no? And if you use the second equation, we know that uh, in the second equation there's no V1. So replacing I2 with the above with this expression, we can cancel the negative. Okay, so we have 5I1 and plus I2, which is I3, 5 plus J2 divided by J2. We cancel out the negative signs, and plus I3 and negative J2. I hope this will work. Okay, so we're down with I1 and I3, and yeah, the same process as before. Transpose the I3 to the other side. 5I1 is equal to this is we bring to the outside the I3, So the rest are negative, no? So you have negative 5 plus J2 divided by J2. This is minus, transpose becomes positive, J2. Okay, and then cross multiply. So you have I1 over I3. Okay, um, so you have J2 minus, I just interchange the two terms, minus 5 plus J2 divided by J2 divided by 5. Okay, so I'm not changing anything, I just interchange the two. Basically they're the same, and we can try calculating it. 2i, sorry, it should be 2i minus 5 plus 2i over 2i, then 5. Oh, I think I made a mistake again. Plus J2 I3. Sorry, I think we missed this one, no? In our equation, we missed this term. So that's why there should be something here. Let's say this is a star, and we use the star here, and actually there's still star here. So we just input the star, and that should be 5 minus 2j. So we 5 minus j2. Okay, sorry for that. This should be 5 minus j2. So we missed the star. So I just write here now. I hope you see the point, and sorry for that. J2. We can replace this one. So my final answer is incorrect. So okay, so therefore this one here is you have 5 minus j2. Okay, then eliminate. So the final answer is times 5 minus 2i. That's right, 33. I think I can show to you the calculator. Let me show you. Okay, so you have here the calculator. I have the transformation r theta, and then you have that one here, 2i minus, then if you press enter, you have the 3.3 angle 90. So this is 3.3 angle 90 degrees. Okay, so I hope you've learned so far the process, no, the process of solving the Hello? I think ako ay try to message. Okay, nakamute ako. Okay, so what was the last time that I was mute? Oh no. Uh, Sorry. Okay, so sorry, I was mute a while ago. I think I pressed the mute. I don't know how long I was mute. Um, Let me check. Can you write the time where I was muted? Can you write in the chat box? Okay, so start of the page, no? Sorry for that. So here, um, yeah, I like to refresh. No? I think you follow me naman in the given. So we just transform this one here, and also the you have. I'm just trying to emphasize that the capacitor acts opposite, no? So if they are in series, okay, so meaning series of force in between the force and the mass, so it acts parallel, no? So the function is parallel. But if it is between the ground, it actually acts like series, no? So you have M here. So the previous example here, you have, well, you have a ground here, and then you have another ground. Okay, so you have ground, and then you have another ground. So it seems like uh, you have a inductor here, which is expressed by mass, and then you have the resistor, which is expressed by, okay, that one, and then the other one. It seems like this is the case, no? Okay, but this is incorrect. Okay, although there's a ground here, there's a ground, but capacitor, okay, acts in series. If they are in parallel, they're actually in series. Okay, so that's the only challenge, no? So this is the correct for this example. This is the correct conversion, okay, for your mechanical tool. um, Analogically, this is also the same with the CR, the one in the rotational spring. So it acts opposite. Okay, so if they are parallel, then they are actually series in the circuit. But if it is connected series, then it acts parallel. So yeah, so this is your. I hope you follow me. Okay, so okay, going back to the problem. So we have CM. Okay, CM, and this is point 0.1, and then the mass here is 5 kj, and but just remember the unit. Okay, so you will not be confused with the unit. So maybe we can write the unit, so to be safe, 10 newton second per meter, and then point 0.1 meter per newton. Okay, and you have the fm there, that the fm is 50 newton. Now, how do you solve this problem? Okay, our goal is, what is the velocity of the mass? Now, the x3 is here. Okay. Okay. Why is it's not here? It's not here also. This is x1, and then this is x2. Okay, be careful with that, no? Because if you notice, this is a spring. The spring has it can compress, and so meaning the x1 dot and then the x3 dot are not the same, because if you punch or if you apply a force with a certain velocity, because of the compression of the spring, okay, it changes the velocity, and x3 is not anymore equal to x1. Okay, so that's the idea there. So that's why it is parallel, no? Because the spring here changes the velocity. So this is the velocity of your force, and the other velocity changes into the spring, right? If you remember, the spring absorbs a force, and we know that this is kx. Okay, so therefore there's a certain displacement, no, for the capacity for the spring. Okay, so there's a displacement because of the incoming force, and that displacement, there's a displacement, and then but there's still a force going to the other side, but it's not anymore the same force. Okay, because the spring absorbs some of the force, no. If you can remember the current, so the current entering from the source is not anymore the same as the current going there, because some of the current going to the capacitor, or in this case spring. So I hope you get that point. So we're looking at x3 dot. Okay, so okay, so since we're looking at the like the current, you can actually, we can actually uh, solve for x3 by two ways, mesh or nodal. Okay, uh, so our goal is x3. Okay, so the first step is actually the transformation. uh, in this case, this is the first step because from the mechanical to electrical. Okay, and then this time the second step is to convert into phasor form. Okay, which is the first part. This is the first step in the previous example. Okay, so if we convert this one, the force is equal to 50, and take note of the unit, Newton. Okay, and you have the capacitor. Now, what is the capacitor? Cm is equal to capacitor. Okay, so uh, so take note of that, no. So that's analogical, no. So meaning the xc here is 1 over j. What is the w? 2, and then jwc, right? So capacitance is 0.1. Okay, so then you have the inductor. The mass here is 5 kilogram. Okay, 5, so therefore this is jwl, so this is j2 times the inductor 5, and then you have the resistance 10 newton second. So if you have kilonewton, so you need to have a uniform unit. So if you are in dynes, for example this is dyne, then you might be using grams and centimeter, and instead of newton, dynes, all of them. Okay, so we call that one the CGS system, the centimeter gram second. And this one here, we call it the MKS, so the meter kilogram second system. Okay, so here MKS, so all of them are in MKS. Mass, meter, sorry, MKS is meter kilogram second. Then so therefore our resistor here is resistor is 10. Okay, and it's a real number. Okay, our goal is to find x3 dot. Okay, since they are analogical, you might use x3 dot as I. Okay, that's the current that we're going to solve. Okay, and how do we can use what method? You can use nodal. You can put a ground here and then for get the voltage here, and you can solve for x3. Maybe we can do that, no, if we still have time, but I think we can solve it one method. Okay, so the easiest method here is the mesh analysis. So loop 1 and loop 2. So at mesh 1, so this is the third step, right? The third step is to analyze the circuit, or solve the circuit, or solve the problem using the analysis that we've learned. So at mesh 1, so you have, so okay, follow the polarity. Now the polarity here, if you notice, it's always positive. Okay, positive, negative, unless if there's negative 50 cosine. Okay, because the signal starts from positive. Okay, cosine starts from positive. Unless if there's a phase difference, but it's always positive here. So that's always positive on that direction. Okay, that's the polarity there is just to indicate which one. Okay, what is the initial polarity. So this is therefore negative 50. Sorry, this should be negative 50 angle 0 or negative 50. That's the same, but it's good to write the angle. Although the angle here is 0, but it's good to write the angle. Okay, uh, plus um, I1 minus so okay, I write the impedance first. 1 over J point 2 and times the I1 minus I2 equals 0. And you arrange the equation I1. Actually, if you calculate this one, this is negative 5 J5. And then for I2 plus I2, which is equal to that's J5, and then transpose the 50, that's 50 angle 0. Then at mesh 2 we have 1 over J 0.2 times I2 minus I1, and then the rest is I2. So we can, there are series, so we can just simply add the two, or you can separate them, no? So we can separate them. It's like J10 I2 plus I10 I2. So but they are the same, no? If we do like this, I2, because they're in series, J10 plus 10, then equals to 0. Okay, so you follow. Okay, actually given this equation here, we can actually have a, we can cancel out the two. We can cancel out the two equation by adding them. You see, because this term here is the same as the term here, except that the I2 here is negative and then the I1 is positive. So if you add that, okay, what I mean here is having derived, you can actually continue and then you can use substitution method. Okay, but here it's obvious that we can directly add them, and then what remains is I2. Okay, if we add it, if we add, this one is negative 50 angle 0, and then this term here and this term here, if you add the two terms cancel, they cancel each other, so plus I2. Okay, by the way, I'm using I2, but I2 is the x3 dot. Okay, so you can actually replace here I2 as x3 dot, and then I1 is x1 dot. Okay, so but I think for you to have a easier solution, okay, then equals to 0. Okay, what I said, you can follow the same style as the our previous lecture. Okay, substitution method, but all it will all come together, no, the same. So okay, so transpose negative 50, so that's 50 angle 0, and then divided by the coefficient here, J10, so that's 10 plus J10, so I just interchange the two. Then using your calculator, so you have 50 angle 0, 10 plus 10i. So this is 3.54 angle negative 45 degrees. Okay, so now since I2, therefore x3 dot is equal to 3.54. Now we follow the same trigonometric values there, cosine 2t. Okay, the same W, the same angular frequency, minus 45 degrees. Okay, and then the unit is, what is the unit of x3? So you remember your the x3. So that's velocity. So that's very simple, meter per second. So you can observe that actually if you want to solve I1, I1 is a little bit higher than 3.54. Okay, if you solve I1 here, that's x3 dot, that's the velocity of the force applied. Okay, so actually it's maybe around 5 cosine something. Okay, and that's angle 0, and here there's a delay. Okay, if you compare x1 dot, okay, it's a challenge to you. You can solve the I1 here. You can solve the I1. Okay, can you do that? Okay, having solved I2, you replace I2 here and I1. So you have a value here, let's say 5 cosine. Obviously the angle here is maybe 0. Okay, the angle here is 0 because it comes from the source, and from the source it should be angle 0, so plus 0 degrees. Okay, so meaning your source, your x1 is from this position. Okay, and then x3 dot is delayed by 45 degrees. Okay, so negative minus 45, so you have sorry, plus advance, that's advance 45, so let's say 45 degrees. So you have that one. So but it's a bit smaller than that, no, than the, so that's, sorry, I think I made a mistake there. um, uh, it should be almost the same case. It should follow the same trend. uh, okay, so something like that. So there's a shift because you can imagine physically that if there's a spring, whatever the speed of your force here, the block, there's a little bit of delay. Okay, and can you imagine if this is cosine, meaning if your force is going back and forth, so your block here is going back and forth but with a delay, no? So meaning the physical meaning of spring gives you a delay. Okay, so that's the idea behind the mechanical rectilinear system, and you can solve those other dynamic systems using the one you've learned in the electrical circuit. Okay, so I think that's all for today, and um, okay, so I hope I have enlightened you a bit. And if you have more questions, so I can give you more examples. Okay, thank you so much, and have a good day to you.